Next is thermal expansion. Before we look at thermal expansion, let's first differentiate two concepts, temperature and heat. It is common knowledge that when it is hot, temperatures are high. It is, however, very subjective to say that it is cold or it is hot. It is much better to indicate the specific temperature, which gives more meaning to such a statement. Temperature is the degree of hotness or coldness of an object on some chosen scale. We measure temperature either on the Celsius or Kelvin scale. Heat is a form of energy that causes a change in temperature. It is a matter of common experience that a solid expands on heating and contracts on cooling. Expansion and contraction could be in length, area, or volume. We use instruments made of different solids in our daily lives. Expansion and contraction of solids are sometimes useful, and at times they pose many technical or engineering problems. To avert any disfiguration of infrastructure, designs must factor in the concept of thermal expansion and contraction. The fact that metals expand on heating and contract on cooling can be demonstrated by this simple experiment. At room temperature, this ball perfectly fits in this ring. Let's see what happens when we hit the ball. You see, the ball just won't fit in the ring, not even we try and force it. But when we cool the ball in cold water, it fits once again. When the ball was heated, it expanded, increasing in its size and therefore would no longer fit into the ring. But when we cool it, it contracts, its size reduces and fits once again. The same would happen if the ring is exposed to temperature changes. Here is the metal ball and the ring. At room temperature, the ball passes easily through the ring. Cool the ring into liquid nitrogen. The ball won't pass because the ring has contracted. The extent of expansion and contraction varies between different materials. This setup can be used to measure the expansion of various materials. Looking closely, we have a piece of aluminium whose expansion we want to measure, and over to the left we have a mechanical amplifier which will indicate the amount of expansion. A slight movement will cause deflection of the needle upwards. The aluminium sample will be heated to show the thermal expansion. And you can already see the deflection of the needle as the aluminium increases in length due to expansion. You can use this setup to measure and compare the expansion of various materials. Just make sure you use equal lengths of the samples. So it is an experimental fact that almost all materials expand when heated and contract when cooled. As heat energy is absorbed, the vibration of the molecules that make up the body is increased. The forces created by increase and decrease in molecular vibrations are an interesting field of study for physicists and engineers. In many cases, the magnitudes of the forces involved can be astounding. To examine these forces, an iron bar will be heated and cooled while the impact of the force generated is observed. The iron bar is designed to rest on a specially constructed fixture that allows one end of the bar to be clamped in a stationary position. The free end of the bar is equipped with an open loop that extends beyond the stop blocks protruding from the fixture. Here's the thick metal bar resting on the fixture. Insert a cast iron pin through the hole. We heat the bar for about 10 minutes. It expands and gets longer, so we can tighten the nuts as the bar cools and watch what happens. As the bar cools, it contracts. The increasing force on the pin eventually snaps it in two. Throughout the heating process, the bar expands as the molecules increase their vibrations. As cold water is poured on the bar, it rapidly vaporizes, removing thermal energy from the bar. The resultant cooling of the bar reduces the energy level of the vibrating molecules, and the bar begins to contract. As the bar contracts, the rod becomes trapped between the iron bar, which is exerting a horizontal force in one direction, and the blocks of the fixture, which are exerting an equivalent force in the opposite direction. As the cooling and contraction continues, slight bending in the iron rod becomes evident. In fact, the iron rod is no match for the forces of thermal contraction and finally gives way altogether. As a material is heated, the frequency and amplitude of molecular vibration increases. The result is thermal expansion. When cooled, the molecular vibrations decrease and the material contracts. The forces generated by the summing up of individual molecular contractions can be quite significant. For instance, the force needed to snap the iron rod in this experiment is approximately 4,000 newtons, a force roughly equivalent to that needed to lift a 1,000-pound mass. Linear expansivity. When a steel rod is heated, it expands. The change in length of the rod is called its linear expansion. The measure of the tendency of a material to expand is called its expansivity. Aluminium expands more than iron, and therefore aluminium has higher expansivity than iron. The table on your screen shows the linear expansivity values of some materials. The knowledge of linear expansivity values is applied in the designing of materials to ensure that they are able to operate well under varying thermal conditions. Ordinary glass expands at a higher rate than Pyrex glass. When hot water is poured into a tumbler made of ordinary glass, it breaks. However, when Pyrex tumbler is used, there is no danger of it cracking. Pyrex glass with its low values of expansivity will not suffer very large forces of expansion as it undergoes temperature change. In building construction, beams can be made out of concrete reinforced with steel because they expand at the same rate. Applications of expansion and contraction in solids. Expansion of solids can cause problems. Railway lines, for example, may buckle during hot weather. So expansion gaps and sliding joints are built into the trackwork. Railway lines are constructed in sections held together by fish plates. The bolt holes are oval shaped to allow free expansion and contraction of the rails with changes in temperature. A more modern method of allowing for expansion in railway lines is to plane the ends of the rails so that they overlap. Pipes carrying steam from boilers are fitted with loops or expansion joints. This allows the pipes to expand and contract easily when steam passes through and when it cools down. Without the loop, the force of expansion and contraction produced would cause breakage of the pipe. Oil is used of this allowance when constructing fuel pipelines. When telephone wires are fixed during a hot day, they are fitted with a sag to allow for contraction when it is cold. If this is not done, the contraction force generated may cause a breakage. Thick metal plates and sheets are joined together by means of rivets. The rivet is fitted when hot and then hammered. On cooling, it contracts, pulling the two plates firmly together. The bimetallic strip. When two metals of different linear expansivity are riveted together, they form a bimetallic strip. Brass and iron are commonly used to make bimetallic strips. On heating the bimetallic strip, brass expands more than iron. The brass thus becomes longer than the iron for the same temperature range. Therefore, the bimetallic strip bends with the brass on the outside of the curve. On cooling, however, the brass contracts more than the iron. It therefore becomes shorter than the iron and thus ends up being on the inner side of the curve. Bimetallic strips have several applications, such as in thermostats and a simple fire alarm. Thermostats are used to control the temperature of electric irons, cookers and fridges, and also in maintaining a steady temperature in a room. Look here. A candle is placed under a bimetallic strip. Can you tell what is happening? The bimetallic strip is working as a switch. Heat from the candle causes the strip to bend downwards. This completes the circuit, supplying power to the motor. The fan then rams, cooling the strip, which then bends upwards, breaking the circuit, and so on and so on. The same happens in a fire alarm. The heat causes bending of the bimetallic strip, completing the circuit, and the alarm rings. Expansion and contraction in liquids. This experiment will demonstrate that liquids expand on heating. We fill 3 vessels with different liquids and suspend them in a water bath. We equalize the level of the liquids in the syringes. Water temperature is 25 degrees Celsius and we have the 3 liquids all at equal volumes. Then we raise the temperature of the water bath. When temperature reaches 30 degrees Celsius, we can already see an increase in volumes of the liquids. Note that the liquids expand at varying rates. So we can conclude that indeed, liquids expand on heating and that the expansion varies from liquid to liquid. Still on the expansion of liquids, let us look at anomalous expansion of water. Usually, solids and liquids expand when heated and contract when cooled. Water, however, shows an anomalous or unusual behavior in that it contracts when its temperature is raised from 0 degrees Celsius to about 4 degrees Celsius. When ice is heated from, say, -20 degrees Celsius, it expands until its temperature reaches 0 degrees Celsius and melts with no change in temperature. The melting is accompanied by contraction. The water formed will still contract as its temperature rises from 0 degrees Celsius. Above 4 degrees Celsius, water expands with increasing temperature just like any other liquid. Since the volume of a given mass of water is a minimum at 4 degrees Celsius, water at this temperature has maximum density, slightly higher than 1 gram per centimeter cubed. Again, during cooling, water contracts with decreasing temperature up to 4 degrees Celsius. Between 4 degrees Celsius and 0 degrees Celsius, there is an abnormal expansion of water instead of the normal contraction. At the melting point of water, that is 0 degrees Celsius, there is a drastic increase in volume, resulting in a large decrease in density as the ice forms. The anomalous expansion of water plays an important role in the survival of aquatic animals and plants during cold seasons. During winter, as the temperature of water decreases, water at the surface of lakes, rivers, seas and oceans starts contracting. As the temperature drops to 4 degrees Celsius, water behaves normally. Its volume decreases and thus its density increases, therefore it sinks to the bottom. This continues until the temperature of all the water falls to 4 degrees Celsius. Now, as the water at the surface cools below 4 degrees Celsius, it expands instead of contracting. Its density decreases. As a result, it becomes lighter than that of the rest of the water and remains floating on the surface. The temperature of this water goes on decreasing to 0 degrees Celsius and finally is converted to ice. Since ice is a bad conductor of heat, water below the surface remains at 4 degrees Celsius, allowing fish and other lives to survive under this water. Expansion and contraction in gases. Gases also expand when heated. This flask is full of cold air. Using my hands, I warm the glass and the tube is dipped into some water. Bubbles soon begin to appear as the air inside the flask begins to expand, forcing its way out of the flask and into the water. If I cool the tube, water is drawn into the capillary as the air inside the flask contracts. This balloon is filled with the gas. Cooling it in liquid nitrogen and the gas contracts. Withdrawing it, the gas expands and the balloon begins to inflate. The particulate nature of matter can be used to explain expansions of solids, liquids, and gases. In solids, the molecules are closely packed and held together by forces of attraction. These forces are so strong that molecules do not change their position but vibrate about their mean positions. When a solid is heated, the vibrations of the molecules increase, resulting in increasing distance from their mean position. This leads to an increase in the size of the solid. In liquids, the forces of attraction between molecules are weaker than in solids. Therefore, liquid molecules are farther apart than in solids. When a liquid is heated in a container, the vibrations of its molecules become more vigorous. The liquid will then occupy more space. In gases, the molecules are much farther apart than in solids and liquids. This is because the attractive forces between gas molecules are very weak. When heated, gas molecules gain more energy and move farther apart, occupying even more space. Measuring temperature. The temperature of a body is measured using an instrument called a thermometer. A liquid like mercury or alcohol is used, and hence the name liquid in glass thermometer. A mercury thermometer consists of a thin glass capillary tube of uniform bore. One end of the capillary tube is drawn into a small cylindrical or spherical bulb. The bulb is filled with mercury. The other end of the tube is sealed. A thick glass stem is used to protect the capillary tube. Commonly used thermometers include clinical thermometer, maximum and minimum thermometer, and the 6's maximum and minimum thermometer. We look at the clinical thermometer. Now, a clinical thermometer, also known as a doctor's thermometer, is a specially designed thermometer used to measure the human body temperature. It consists of a capillary tube of fine bore. It is enclosed in a glass tube on which a scale is mounted. This glass tube is called the stem of the thermometer. The convex side of the stem acts as a magnifier so that the mercury thread is seen easily. One end of the capillary is drawn into a small cylindrical or spherical bulb. The bulb is filled with mercury. The other end is sealed. There is a constriction present in the capillary tube a little beyond the bulb. The mercury passes through this constriction only when it expands due to the rise in temperature. The mercury thread remains in its position due to this constriction, and the temperature can be easily read. There is a mark on the stem of the thermometer which indicates the normal body temperature. To take the body temperature, the thermometer is placed under the armpits or below the tongue. The thermometer must be sterilized before and after use using an antiseptic solution. It should not be washed with boiling water, since this could cause breakage due to extreme expansion of mercury. The thermometer has to be jerked to force the mercury back into the bulb before use. It is calibrated either in degrees Celsius or degrees Fahrenheit. Presently, there is an LCD thermometer in use. Then we have the bimetallic thermometer. And this type of thermometer consists of a coiled bimetallic strip. One end of the strip is fixed while a pointer is attached to the other end. An increase in temperature makes the spiral to curl in a clockwise direction, forcing the pointer to move over the calibrated scale. The curling is due to the unequal expansion of the material in the bimetallic strip.
The importance and role of communications through broadcasting. I learned that.
Understanding the balance between vision and expression. I learned that.
Exploring the issues of our time. I learned that.
How to think like a great designer. I learned that.
Integrating creativity with professionalism. I learned that.
That's where I learned.